Ever wondered how water gets to your shower? Or maybe why blood moves through your veins the way it does? What if we told you the same fundamental physics is at play in both? Today, we're diving deep into the fascinating world of internal fluid flow. That's basically when a fluid completely fills whatever path it's in, like, a pipe or a blood vessel. Our mission here isn't really to walk you through a textbook step by step. It's more about giving you a shortcut to understanding the most important nuggets of knowledge from our sources, turning those complex ideas into, hopefully, some satisfying aha moments you'll actually remember.
Absolutely. We'll be exploring quite a range, everything from the fundamental differences between smooth, orderly flow and that kind of chaotic, messy movement. We'll look at how engineers design these massive pipelines, for oil or water, and fascinatingly, how medical researchers are applying these exact same principles to understand the flow within your own body. We've got some, I think, quite surprising facts that really connect these dots, showing you just how vital this field is in shaping our world.
Okay, let's unpack this a bit. Think about, say, cigarette smoke rising. At first, it's this perfectly smooth, almost elegant plume, right? Then almost suddenly, it just starts to get all chaotic, swirling and fluctuating in every direction. That feels like a pretty good analogy for what happens inside pipes.
It's a perfect analogy, actually. That distinction is absolutely foundational in fluid mechanics. At lower velocities, the fluid flow is what we call laminar. It's characterized by smooth, parallel streamlines. You can imagine layers of fluid just sliding neatly past each other, almost like a deck of cards, very orderly. But you increase that velocity, and it becomes turbulent. That's marked by these velocity fluctuations and highly disordered motion, like swirling eddies. And honestly, most flows you encounter in daily life, they're turbulent. Your tap water, oil in a refinery pipe, air from a fan, mostly turbulent.
So, okay, it's one thing to see this transition, from smooth to chaotic. But how do engineers actually predict when that's going to happen? Is there like a specific point, a magic number?
There is, and it's a really critical one, the Reynolds number. It's what we call a dimensionless quantity, so no units, and it essentially balances the fluid's inertia, its tendency to keep going against its viscosity, its internal friction or stickiness. Osborne Reynolds himself, a British engineer back in the 1880s, he very elegantly confirmed these regimes. He did these experiments injecting dye into glass pipes, very visual, and he observed that at a certain critical Reynolds number, the flow just fundamentally changes character. Now, for typical circular pipes, that critical value is generally accepted as being around 2300. So below 2300, it's pretty reliably laminar. Above about 4000, it's definitely turbulent.
And what about in between, like 2300 to 4000?
That's the transitional zone. It's a bit unpredictable there. It can switch back and forth between laminar and turbulent. And look, this shift isn't just, a scientific curiosity. It's fundamental to engineering design. Because when flow turns turbulent, that increased mixing, all those eddies, radically changes how much energy you need to push that fluid. It demands far more pumping power. So this single concept captured by the Reynolds number dictates huge decisions. Everything from city water grids to how oil pipelines are designed. It directly impacts efficiency and, importantly, energy costs.
Okay, so what does this mean for a fluid just entering a pipe, like for the very first time? We know about the no-slip condition, right? The idea that fluid literally sticks to the pipe wall, zero velocity there.
Yeah.
How does that influence the flow as it travels further down the pipe? Does the flow pattern eventually settle down?
Yeah, it's a really fascinating process right at the entrance. Because the fluid right at the wall comes to a complete stop, it exerts a drag on the adjacent layers, slowing them down too. Now, to maintain the same amount of fluid moving through the mass flow rate, the fluid in the center of the pipe actually has to speed up to compensate. And this creates what we call a velocity boundary layer. It's this region near the wall where these viscous shearing forces are most significant, where the velocity is changing rapidly from zero at the wall to faster speeds towards the center.
So it's like the flow profile is constantly evolving as it moves down the pipe, at least initially.
Exactly right. That region from the pipe's entrance until this velocity profile stops changing and fills the entire pipe. That's called the hydrodynamic entrance region. After this point, you enter the fully developed region. Here, the shape of the velocity profile stays constant. For laminar flow, that shape is a nice, smooth parabola. But for turbulent flow, because of all that mixing from the eddies, it's much flatter, much fuller across the pipe diameter. And what's interesting is that the friction at the pipe surface, what we call the wall shear stress, it's actually highest right at the pipe inlet.
Oh, really? Not further down?
No, right at the start where that boundary layer is first forming. Then it gradually decreases until it becomes constant in that fully developed region. This means the pressure drop is higher in these entrance regions. Now, for really long pipes, it might not matter much overall, but for short pipes, that entrance effect can be surprisingly significant in the total pressure loss.
And how long is this entrance region typically?
Well, it depends heavily on the flow regime. For engineers, knowing this length is important. In turbulent flow, the entry length is actually surprisingly short. Often it becomes pretty insignificant after just about 10 pipe diameters, so LH over D less than 10. But for laminar flow, it can be much, much longer. Maybe up to 115 diameters for a Reynolds number, right at that critical point of 2300. It can take a really long time for that flow to truly settle down if it's laminar.
Okay, so let's talk about the practical side. Moving fluid, whether it's water coming into your home or, oil across an entire country, that requires energy, right? We're talking about overcoming pressure drop. What's the real cost here?
The pressure drop due to these viscous effects, the friction, represents an irreversible energy loss. It's energy you have to continually put in just to keep the fluid moving. Now, for laminar flow in a standard circular pipe, this pressure drop is proportional to a few things: the fluid's viscosity, the pipe's length, the average velocity. But here's the kicker, the really important part. It's inversely proportional to the square of the pipe's diameter.
The square.
Okay, right. And this leads directly to a crucial principle known as Poiseuille's law. What it tells us is that for a specific required flow rate, the pumping power needed is inversely proportional to the fourth power of the pipe's diameter.
Wait, hang on. The fourth power, not the square, the fourth.
Yeah, fourth power.
Wow. So let me get this straight. If you double the pipe diameter, you reduce the pumping power needed by a factor of 16.
16, exactly.
That's genuinely huge.
Yeah.
It really makes you think about the engineering decision behind every water main or oil pipeline we see. I mean, that law must have saved just countless hours and millions in energy costs over the decades just by choosing slightly larger pipes.
It absolutely has. This is precisely why engineers have to carefully weigh the initial cost of a larger pipe against the significant long-term savings in energy costs. It's a fundamental trade-off. Now, how do we express this energy cost more generally, covering both laminar and turbulent flows? We use something called the Darcy friction factor, often just called F. This factor allows us to calculate the pressure loss and also something called head loss. Head loss, usually written as HL, is a really useful concept. It literally represents the additional height a pump would need to lift the fluid just to overcome all that friction in the pipes and fittings. It puts the energy loss into a physical height equivalent.
Okay, so F, the friction factor. And you mentioned turbulent flow is different. Does the pipe surface itself come into play more, like if it's not perfectly smooth?
It certainly does. That's a key difference. Unlike laminar flow, where the friction factor for a circular pipe is simply a function of the Reynolds number, actually, it's just 64 divided by the Reynolds number. In turbulent flow, that friction factor F becomes a very strong function of the pipe's surface roughness. Why? Because in turbulent flow, there's a very thin layer near the wall, the viscous sublayer, where the flow is still somewhat smooth. But the tiny hills and valleys of the pipe's roughness can actually protrude through this thin layer, significantly disrupting the flow and increasing turbulence near the wall.
So a rougher pipe means more turbulence near the wall, which means more friction, more energy loss.
Exactly. More head loss, higher printing costs.
Yeah.
To handle this complexity, engineers rely heavily on a critical tool: the Moody chart. You'll see this in any fluids textbook. This chart is a masterpiece, really. It's based on tons of experimental data and also on a complex implicit equation called the Colebrook equation. What the Moody chart does is graphically present that friction factor F as a function of both the Reynolds number and the pipe's relative roughness. Relative roughness is just the absolute roughness height, like the average height of those bumps, divided by the pipe diameter.
So it combines everything: flow speed, fluid properties, pipe size, and roughness into one chart to find that friction factor.
Precisely. Now, that Colebrook equation itself, the basis for the chart, is implicit. That means F appears on both sides of the equation, so you can't solve for it directly. You often need to iterate, guess a value, and refine it. Thankfully, there are some very good explicit approximations, like the Hallan relation, that can get you within, say, 2% of the exact answer without needing iteration. Very handy for quick calculations. But this whole framework, Reynolds number, relative roughness, Moody chart, or Colebrook equation, it allows engineers to solve the three fundamental types of pipe flow problems. You can calculate the pressure drop if you know the flow rate and pipe details. You can determine the flow rate you'll get for a given pressure drop, Or, crucially, you can figure out the right pipe diameter needed to achieve a desired flow rate with an acceptable pressure drop. It's really incredible how a single chart developed decades ago still underpins so much practical engineering.
Okay, but pipes aren't always perfectly straight, long sections, are they? What happens when the fluid hits, like an elbow or goes through a valve, or the pipe suddenly gets wider or narrower? Do those add to the cost?
Oh, absolutely they do. That's where minor losses come into play. Now, the name minor can be a bit misleading. While they might be small compared to the friction loss in, say, a mile-long straight pipe. In systems with lots of fittings, elbows, T's, valves, inlets, exits crammed into a relatively short distance, these so-called minor losses can actually be the dominant source of head loss. They can add up very quickly.
So why do they happen? What's the physics there?
They primarily happen because of flow separation and the intense mixing that results. Think about a sharp-edged pipe inlet versus one that's nicely rounded. With a sharp edge, the fluid can't make that sharp 90-degree turn instantly. The flow separates from the corner, constricts into a narrower stream inside the pipe called a vena contracta, and then it expands again. This separation and re-expansion causes a lot of turbulence and energy dissipation. A sharp inlet might have a loss coefficient, KL, of about 0.5.
What does that mean, KL equals 0.5?
It means that the head loss caused by that fitting is equal to 0.5 times the velocity head, which is v squared over 2g. So basically, half of the fluid's kinetic energy is lost right there at the entrance. But if you just slightly round that inlet edge, say with a radius that's maybe 10% of the pipe diameter, that KL value drops dramatically, maybe down to 0.12 or even less. It shows how small design changes, paying attention to smooth transitions, can lead to huge gains in efficiency. And here's an interesting one. At a pipe exit, where the fluid discharges into a large tank or reservoir, nearly all of the fluid's kinetic energy is considered lost as it mixes turbulently with the surrounding fluid. The loss coefficient KL there is approximately 1.0 for turbulent flow. And unlike the inlet, it doesn't matter if the exit is sharp or rounded. There's no advantage to rounding an exit in terms of reducing this particular loss. That's a common misconception.
Huh. Okay, that's counterintuitive. So we quantify these with a loss coefficient, KL. And valves must have KL values too.
Definitely. Valves are essentially devices designed to introduce a controllable minor loss. That's how they regulate flow. A fully open ball valve, for example, is very streamlined. It has a very low KL, maybe around 0.05, causes minimal disruption. But take something like a globe valve, even fully open, it forces the fluid through a more tortuous path, so its KL might be around 10. And if you start closing that globe valve, say 3/4 closed, the KL value can shoot up enormously, maybe to 17 or even higher, creating tremendous resistance and drastically cutting the flow rate.
So, okay, we have friction losses in straight pipes and these minor losses in fittings. What happens when we start connecting all these pieces together into a bigger system, a network?
Right, that forms a piping network. And how we analyze it depends on how the pipes are connected. For pipes connected in series, one after the other, it's fairly straightforward. The flow rate has to be the same through each section, right? Conservation of mass. And the total head loss for the whole series is simply the sum of the friction losses in each straight section plus the sum of all the minor losses from all the fittings. You just add them all up. But for pipes connected in parallel, where the flow splits, goes through multiple branches and then rejoins, it's different.
How so?
Well, the total flow rate splits among the branches. But the key principle here is that the pressure drop, or equivalently the head loss, across each parallel branch must be identical. The flow will automatically distribute itself among the branches to satisfy this condition. It's very similar to Kirchhoff's voltage law in electrical circuits, where the voltage drop across parallel resistors is the same.
Ah, okay, so you can think of flow rate like electric current and pressure drop like voltage.
Exactly. It's a useful analogy. The main challenge, though, is that the resistance to flow in a pipe isn't constant like electrical resistance. It depends on the flow rate itself because of the friction factor changing with Reynolds number, especially in turbulent flow. This nonlinearity makes analyzing complex networks tricky. You often need iterative methods or specialized computer software to solve them accurately.
And then, of course, you often need to add a pump to the system, right? To move fluid uphill or just overcome all these losses over long distances.
Yeah.
How do engineers figure out what size pump they actually need?
Precisely. A pump adds energy to the fluid. For a typical system, say pumping fluid from a lower reservoir to a higher one, the useful head the pump needs to provide has to be enough to lift the fluid against gravity, that's the elevation difference, plus it has to overcome the total head loss in the entire piping system, all the friction and minor losses. So engineers first determine the system curve. This curve shows how much head is required by the piping system itself at different possible flow rates. As flow rate increases, head loss increases, usually quadratically, so the system curve slopes upward. Then they look at pump characteristic curves. These are provided by pump manufacturers and show how much head a specific pump can actually deliver at different flow rates. Typically, a pump delivers less head as the flow rate increases, the point where the system curve intersects the pump curve. That's the operating point.
The sweet spot.
Exactly. That's the actual flow rate and head at which that specific pump will operate in that specific piping system. It tells the engineer if the chosen pump is suitable for the job.
This has all been fascinating, really digging into controlling and designing flow. But how do we actually measure it, especially inside a pipe? What are the tools that let us quantify these often unseen forces?
Right, measurement is crucial. There's a really wide array of devices, from the very simple to the incredibly sophisticated. I mean, the simplest method for, say, a garden hose is just timing how long it takes to fill a bucket of a known volume. But for more precise or industrial applications, we usually measure velocity and then calculate the flow rate from that. Pitot-static probes are very common. Named after Henri Pitot and later refined by Henry Darcy, names we keep hearing. They're simple, reliable, been around forever. They work by measuring the difference between the stagnation pressure, the pressure when the fluid is brought to a stop right at the probe tip, and the static pressure of the surrounding flow. That pressure difference is directly related to the local fluid velocity.
Okay, and what about meters that measure the overall flow rate directly?
Yeah, there are many types. Obstruction flow meters are a big category. These include things like the orifice meter, the Venturi meter, and the nozzle meter. They all work by deliberately constricting the flow path. This forces the fluid to speed up through the constriction, which causes a drop in pressure, according to Bernoulli's principle. By measuring the pressure drop across the obstruction, you can infer the flow rate. The Venturi meter is generally considered the most accurate and causes the least permanent head loss because its gradual expansion section helps prevent flow separation. It's streamlined. Its discharge coefficient, CD, is very high, like 0.95 to 0.99. Then you have positive displacement flow meters. Think about the meter at a gasoline pump.
Yeah. The ones that click.
Exactly. They work by continuously trapping and discharging known volumes of fluid in little chambers. They directly measure the total volume that has passed through, very accurately for billing purposes. There are also turbine flow meters, which have a little propeller or turbine inside that spins as fluid passes. The rotation rate is proportional to the flow rate. And rotameters, which are often used in labs, they're those simple, vertical, tapered glass tubes with a float inside. The faster the flow, the higher the float rises. Very visual, direct reading.
Okay, those sound like the workhorses. But what about the really cutting-edge techniques? You mentioned seeing the flow. How do we get closer to actually visualizing this invisible movement?
Absolutely. This is where things get really exciting. Ultrasonic flow meters are a fantastic example of non-intrusive measurement. They can often just clamp onto the outside of an existing pipe, no need to cut into it, no need to stop the process. They work by sending ultrasonic sound pulses through the fluid. Some measure the difference in travel time for pulses going with the flow versus against the flow. Others use a Doppler effect, measuring the frequency shift of sound waves reflected off particles or bubbles in the fluid. It's similar to how a radar gun catches speeders, or how the pitch of an ambulance siren changes as it passes you.
Wow, so no interruption, no pressure drop. That must be huge for certain industries, like maybe chemicals or food processing.
Exactly. They are great for corrosive fluids, even slurries where other meters might get clogged or damaged. And causing zero pressure drop is a big energy-saving bonus. Another really advanced technique is thermal anemometry. This uses incredibly tiny electrically heated wires or thin films placed in the flow. The instrument measures how much electrical power is needed to keep that tiny sensor at a constant temperature as the flowing fluid cools it down. More flow means more cooling. This allows for extremely precise, almost instantaneous velocity measurements right at a single point. They're so fast they can even capture the rapid fluctuations in turbulent flow, measuring thousands of times per second. But perhaps the most visually stunning methods, the ones that really let us see the flow, are laser Doppler velocimetry, or LDV, and particle image velocimetry, or PIV. LDV uses intersecting laser beams to create a tiny measurement volume. When small seeding particles naturally present or added to the flow pass through this volume, they scatter light. By analyzing the frequency shift of the scattered light again, the Doppler effect LDV can measure the velocity at that single point with very high accuracy and without disturbing the flow. And then there's PIV. This is often called a whole field technique.
Whole field. What does that mean?
It means instead of measuring velocity at just one point like LDV or a pitot probe, PIV captures the velocity across an entire plane or area of the flow simultaneously. How it works is you seed the flow with tiny particles again. Then you illuminate a plane within the flow with two very quick, intense pulses of laser light, like a double flash photograph. You capture two images of the particles very close together in time. Then, sophisticated software analyzes these two images, tracks the movement of particle groups between the flashes, and calculates the velocity vector for hundreds or even thousands of points across that entire illuminated plane. It's literally like taking an instantaneous snapshot of the entire velocity field. You get these amazing maps showing vectors, streamlines, vortices. It truly makes the unseen visible.
That's incredible. PIV sounds revolutionary. And this whole deep dive, all these principles, it really comes to life when you stop and realize that the human body is maybe the most incredible, complex piping network of all.
It truly is. Our cardiovascular system is just a prime example of everything we've been discussing. The heart is the pump, a remarkably sophisticated one. Our arteries, veins, capillaries, those are the pipes. And our heart valves, they function exactly like the valves we talked about, controlling flow direction. But it's far more intricate than any industrial system we could build. For one thing, our vessels aren't rigid pipes, they're compliant. They stretch and relax with each heartbeat to smooth out the pressure pulse. And the flow itself isn't steady, it's highly pulsatile, driven by the rhythmic contractions of the heart. This creates complex wave phenomena, pressure waves, and flow waves traveling and reflecting throughout the vascular network. Think about the scale, too. The aorta, the main artery leaving the heart, starts at maybe 25 millimeters in diameter. It branches and branches, continually tapering down until you reach the capillaries, which are tiny, maybe only 5 microns in diameter, just wide enough for red blood cells to squeeze through single file. Then the network collects again, vessels gradually getting larger, eventually returning blood to the heart through the vena cava, which is back up to about 25 millimeters. It's an amazing feat of biological engineering.
So, given this complexity, how are researchers actually using these advanced fluid mechanics techniques like PIV you just mentioned to understand what's happening inside us and maybe improve medical devices?
It's a hugely important and rapidly growing field, biomedical fluid mechanics. For example, work done at places like Penn State has used PIV and LDV extensively in the design and testing of pulsatile pediatric ventricular assist devices, VADs. These are basically temporary artificial heart pumps for children who are waiting for a heart transplant. It's critical work. By using PIV to visualize the flow patterns inside these tiny complex pumps, especially looking at the formation and movement of vortical structures, those swirling regions of fluid, engineers can optimize the pump geometry to minimize areas where blood might stagnate or experience very high shear stress. The big goal is to prevent blood clots from forming on the device surfaces, which is a major life-threatening risk with any artificial heart component.
So they're literally watching the flow inside the device to make it safer.
Exactly. They've also used LDV, for instance, to study the flow within the housing of mechanical heart valves. They might focus on the tiny gap when the valve leaflet closes, measuring the intense vortex that gets created right at the moment of impact. By analyzing the duration and the magnitude of the shear stresses in that vortex, they can estimate the potential for damage to red blood cells passing through. It gets down to that level of detail, and it all comes back to the fundamental principles. Remember, conservation of mass. We can apply it directly. Consider the aorta branching in your pelvis into the left and right common iliac arteries heading towards your legs. If we know the diameter and average blood velocity in the aorta just before the split, say 15 millimeter diameter, 30 centimeters velocity, and we measure the diameter and velocity in the left iliac artery, maybe 8 millimeter, 40 centimeters, then just using conservation of mass flow and equals flow out, we can calculate what the velocity must be in the right iliac artery if we know its diameter, say 10 millimeter. It works out to about 41.9 centimeters in this example. Simple principle, powerful application.
That's just incredible, using these core engineering principles, coupled with advanced visualization, to literally see and understand the flow within us. It's leading to better diagnostics, safer implants, truly life-saving technologies. Even things like magnetic resonance imaging, MRI, have been adapted now. There are techniques, phase contrast MRI, that can actually measure the 3D velocity field of blood flowing through a living human heart non-invasively. It reveals these complex, subtle helical flow paths that doctors think are important for efficiency in preventing disease. It can help diagnose conditions like pulmonary hypertension just by looking at the flow patterns. It really brings the science to life in a profound way. So it seems from the absolutely massive pipes carrying oil across continents, down to the microscopic capillaries delivering oxygen in your own body, the fundamental principles of internal fluid flow govern it all.
Understanding this dance between smooth laminar flow and chaotic turbulent flow, realizing the constant energy cost of friction, and seeing how we measure these often unseen forces. It really gives you a deeper appreciation for both the engineered world around you and maybe even the incredibly complex biological systems within you.
I think what's truly profound here is how this branch of physics, fluid mechanics, gives us the tools to model, predict, and actually optimize systems that are just incredibly diverse. City water networks, jet engine fuel lines, chemical reactors, and yes, the most complex biological fluid transport systems known. It really is a testament to the universal language of science and engineering.
Well, we certainly hope this deep dive has given you some, perhaps, unexpected aha moments and maybe a new perspective on how these fluid dynamics really do shape our world in countless ways.
And maybe next time you hear your own heartbeat, just take a second to consider the incredibly intricate fluid mechanics happening right there. This amazing system constantly adapting and optimizing flow with every single pulse. It makes you wonder what other unseen flows are happening all around us right now that we just never stop to consider.